We're going to do one last example of using the rational zero theorem to help us solve a polynomial equation. Notice that sometimes the rational zero theorem gives us the kickstart to the problem, and then we rely on other algebra knowledge. So that'll probably be the case as we look at this next example. So we're going to solve this time x to the fourth plus x cubed minus 5x squared plus x minus 6 equals 0. So basically this is no different than saying find the zeros of the polynomial. Sometimes the wording of it can make us feel like we're doing different things, but it's really equivalent. So complex polynomial, right? I mean, it looks kind of messy. And we can start with using this idea of possible zeros. That idea of possible zeros will get us off to a good start, and then we can fill in with other things as needed. Possible zeros goes back to the idea of P over Q. Just to remind us of that process, right? We're looking at the factors of -6 divided by factors of, in this case, right, 1 is the coefficient on our highest powered term. So I'm going to list those out. For -6, thinking about factors, we could have plus or minus 1. We could have plus or minus 2, plus or minus 3, plus or minus 6. So those would be the factors of -6. In the denominator, not too bad, factors of 1, just plus or minus 1. So, of course, dividing the numerator by plus or minus 1 really doesn't change anything. So we really just end up with plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. And depending upon who you are, you may benefit from being a little bit more specific with that, listing out 1, -1, 2, -2, 3, -3, 6, -6. So I ended up with a list of 1, 2, 3, 4, 5, 6, 7, 8 possible zeros. I know this polynomial has only 4 zeros, right? And these are 8 possible rational zeros, but we know that it could have irrational zeros like we saw in the last video, or another option is you could even have imaginary zeros or complex zeros. So we'll just kind of watch out for what happens as we move through. Cool. So based on this list, again, you might just be somebody who pushes through from beginning to end until you get your remainder of 0. It's not a bad idea, kind of brute forcing it. Some people just dive in the middle of the list, so you really can do whatever's easiest for you. I'll go ahead and just start at the beginning because I think that's what a lot of you would do. So make sure you have this function written down because I'm going to need these values to set up the synthetic division, and then we'll just start showing the work. So let's start by trying x equals 1. So I'm going to use that as my first starting point. So set up the synthetic division. You guys have the function written down, so I'm not going to keep scrolling up and down. But the placeholders for the function were 1, 1, -5, 1, and -6. I'm dividing by 1. So at this point, I'm not going to elaborate too much on this process. I know you guys are well experienced by this point with synthetic division, but I'm just going to carefully show my steps, trying not to make any goofy arithmetic errors. Let's see, -5 plus 2 sounds like -3. Multiply that, we get -3. Add, we get -2. Multiply, add. Bummer. So my remainder for my first attempt is -8. Remember, our desire is to get a remainder of 0 because only then does that mean we've found a true 0 for the polynomial. So no problem. 1 didn't work. Maybe try -1. So I'll just keep trying until I hit a remainder of 0. Or if you just get kind of frustrated with the process, you can bounce around a little bit more. You don't have to go in order of that list, but sometimes being methodical helps. So same beginning, 1, 1, -5, 1, -6. Now we're dividing by -1. So drop, multiply, add, multiply, add, multiply, add, multiply. Oh, so close. Bummer. So if the sign had been different, we would have been in business, but it looks like here we're getting a remainder of negative 12, which again is not 0. Okay, so we tried 1, we tried negative 1. Neither of those were good to go because we didn't get remainders of 0, but next in our list was 2, so I'm just going to try 2 next. So this is building good persistence, right? So let's try x equals 2 with our synthetic division. So same starting point, 1, 1, negative 5, 1, negative 6. We're dividing this time by 2. So again, I'm just going to move through that synthetic as if we're pros at it because we've been doing it for a little while. Honestly, for me, the hardest part is keeping the color coding going. So I'm dropping, I'm multiplying, I'm adding, I'm multiplying, I'm adding, I'm multiplying, I'm adding, I'm multiplying, and I'm adding. Yay, we get a 0, right? So a little bit of excitement. We got our first 0 for the polynomial. Of course, this is a rational 0. So far we know x equals 2 is one of the 4 zeros for this polynomial equation. So I'm going to kind of guide our discussion a little bit. You can take several different approaches to keep finding zeros, but I'd like to demonstrate one thing that's kind of neat. So I'm going to make a really good guess for this next 0. I'm actually picking something that I know is going to work, so mostly just to demonstrate a point with you all. So we used 2, we got a 0. That means what I'm allowed to do now is continue dividing from where I left off. So I want to illustrate this with you guys. I don't have to keep starting from the beginning now as I try another 0. So using the remainder of dividing by 2, I'm going to go ahead and show how we can just continue building off of that synthetic division to continue breaking down our function. So I'm going to drop multiply, messing up our color coding here, so let me try a little better. Multiply, add, multiply, add, multiply, and add. So we get a 0 again, right? So this means that not only is x equals 2 a 0, but x equals negative 3 is also a 0. So again, you might not have done negative 3 next, right? I kind of skipped around in my list a little bit, but I wanted to demonstrate how we can do our synthetic division from where we left off rather than from the beginning. So let's summarize where we are, because I know on my screen you can't see all that we've done. But what I'm going to do is on this next screen here, rewrite the original problem. A lot of times it helps to just reframe where we are. So the original was x to the 4th plus x to the 3rd, minus a 5x squared plus x minus 6 equals 0. When we divided by 2, right, the corresponding factor would be x minus 2. The remainder, and you can go back to your synthetic division to verify this, would have been an x cubed plus a 3x squared plus an x plus a 3. And that just came from, again, basically I'm stealing these here to be the placeholders. And then we synthetically divide it again with negative 3, which means the corresponding factor would be x plus 3. And what we were left with was an x squared plus 1. So let me just go back and make sure you guys see that x squared plus 1. So this was an x cubed term. So when we divide, this is an x squared, x, our constant term. So 1x squared plus 0x plus 1 is what remained. And there that is right there. Cool. So at this point, I guess what I'm trying to say is there's no need to continue using the rational zero theorem in fact, the remaining two zeros aren't going to be rational. So I would say the rational zero theorem has done its job. We know for a fact that x equals 2 is a rational zero, and we know for a fact that x equals -3 is a rational zero. This degree 4 polynomial will have a total of 4 zeros, right? It doesn't mean they're all going to be rational, but 4 zeros in total. So the remaining two zeros are hiding out in this little quadratic piece. So let's just chat about x squared plus 1 equals 0. A lot of you would probably subtract 1 from both sides and use the square root property to solve this. So all I'm going to do is square root both sides, and we are now into imaginary territory, right? The square root of a negative number is not real. So by definition, the square root of -1 is actually just I. So it looks like our remaining two zeros are plus I and minus I. So I'll just write those out separately so we can stare at them together, plus I and minus I. And my 4 red boxes are the 4 zeros of the polynomial. So we used the rational zero theorem to find the first two zeros, and then we just built off of our prior algebra experience to find the last two. And I'm going to run out and graph this because I haven't graphed something for you guys in a while, and let's just connect the dots graphically as well. Be right back with that graph. Okay, so I have the graph ready to go. I just used Desmos. And you can see here that one of the zeros, right, one of the places we cross the x-axis is at x equals -3. That was one of the rational zeros we found. We also see another zero at x equals 2. So if you're concerned about the other two zeros, we have to remember that when we graph, we're graphing on the real number plane. You can take other classes where you actually graph on the complex or imaginary number plane as well. But the reason we don't see I and -I as visual locations where we cross the x-axis is because this is the real number plane. So just so we're aware of that, you won't always visually see all your zeros, particularly you won't see them if they're imaginary or what we call complex. So one last thought to leave you with, and that is when you have zeros that are not rational or irrational, they're complex. And there's this really cool theorem which says that if you have one imaginary zero, you've got to have its conjugate. So imaginary zeros, in other words, only come in pairs. So I'll write this theorem out specifically. And it says if a plus bi is a zero of the polynomial, so I'll just make sure we're clear, it's a polynomial function, f, with real coefficients, so the function itself has real coefficients, then we can guarantee ourselves that the conjugate of that zero is also a zero. So then I can say, then so is a minus bi. So if you have a plus bi as 1, 0, the conjugate is just changing the sign in the middle, and that's a guaranteed 0 as well. So that's a pretty handy thing anytime you've got imaginary zeros. All right, that is the rational zero theorem and a little bit more. So have some fun practicing.